Okay, here we're going to look at two ways to calculate a moment. So this is going to really emphasize how moment arms and forces matter. And so remember, the moment arm is perpendicular to the line of action of the force. So here we just use a person with their arm abducted 60 degrees. We see the length of the arm, the vertical force, that's a weight in the hand, and it makes sense that the moment arm is perpendicular to the axis of rotation at the shoulder, okay, and we can see the distance here. So if we write it out and plug this in, we can say, okay, so we've got, the force, the length, the force of the load times the moment arm of the load, right? Okay, but look, if we have to actually calculate that, we can say, all right, well, how do we get this moment arm length? Well, we got the length of the arm, so we got to know the angle, 60 degrees. So we can use our geometry, our trig, and calculate, sine 60 times the length of the arm. That'd give us the moment arm. So we can kind of see that here. Moment arm length equals length of the arm times sine 60. Then we plug that into our external moment equation. We get the force of the load times the moment arm, which is the length of the arm times sine 60. Okay, fine. Okay, so that all makes sense. So let's look at it done just a little differently. The same exact situation, but done a little differently. Essentially, what we could see here is the axis again, but now the moment arm I've drawn differently. So to use this moment arm, what we're going to do is resolve the forces into parallel and perpendicular components. So we know that the angle of the arm is at 60 degrees. So this force can be decomposed into forces acting along this segment up to the shoulder and then also perpendicular to the segment. So if we wanted to do that, we could say, okay, what's this force perpendicular to this segment? We know that this inside angle here is 60 degrees. So yeah, force of the load sine 60 equals the rotary component, or the force that's perpendicular to this segment. Okay, and the perpendicular distance from the rotary force, this vertical force acting along this line, up to the axis is the length of the arm. So we can plug that all in. So we have the force of the load that's perpendicular here times the moment arm. We know that the moment arm in this case equals the length of the arm, so put length of the arm here, and then essentially we get force of the load times sine 60 and length of the arm. So if you look at the other equation, they're exactly the same. So essentially, as long as you are consistent in using a perpendicular distance for your moment arm and your the correct load or line of action that's a rotary component that you're interested in, you'll come up with the same answer.